Okay, for this first question, there is automatic transmission fluid located inside of an oil pan underneath a car, and the fluid is cooled using 100 kilometer per hour air flowing underneath of it. And you're asked to find the convective heat transfer coefficient or convective heat transfer rate from the surface of the pan to the surroundings. You can assume that this process is steady state and that the temperature is constant on the surface. And for the temperatures, you use the average temperature to get properties. And then external forced convection shows up in this equation because you have to find the heat transfer coefficient of air. And so you can start by finding the Reynolds number and determine whether it's laminar or turbulent. And then from that, you can find the Nusselt number, and then that leads you to the heat transfer coefficient. And then convection shows up in this question because you use Newton's law of cooling to find the convective heat transfer rate. And this is the value that you get. For the second question, it uses the same oil pan from above, but now you're trying to solve for the time it takes for the surface of the pan to reach 150 degrees Celsius when the car is stopped but still running. So there's no longer airflow on the outside. And for part A, you use the lumped analysis equations. So that's where zero-dimensional transient heat transfer shows up. And first you find the characteristic length, which is just the half thickness, because there's thermal symmetry at the center. And then you find the BO number, which is greater than 0.1. And so this means that this is only a rough approximation, but that is why we use the one-dimensional analysis in the second part, because it has a better approximation. And then you solve for B and plug that into this equation to solve for T. And you get 7.02 milliseconds. And then for part B, this is where the one-dimensional transient heat transfer comes up. The BO number is the same, and then you use that value in table 4-2 to find lambda and A1. And then from that, you can solve for tau using this equation. And tau is greater than 0.2, so this one-dimensional approximation is okay. And then using the tau equation, you can solve for time. And you get 29.7 milliseconds. So this is a big difference in terms of milliseconds, but since the dimensions are so small, it's likely that this difference is not going to be observable. Okay, for question 3, there's a lava lamp that works by using natural convection currents because there's a cold surface at the top and a warm surface at the bottom. And so these differences in density naturally allow the fluid to rise and fall. And so if we assume that this fluid is mostly water, or if we look at just the water, then we can find the heat transfer rate for conduction using this natural convection current, because we can model this process, this convective process, as conductive using a certain thermal conductivity. And so you use the film temperature for properties. We can also assume that the radiation effects are negligible and the surface temperatures are uniform. And to solve this, natural convection shows up in this question because you have to find the Nusselt number for natural convection. And so using that handout, we can use the equations for natural convection to find the Rayleigh number. And then since it's between this range, then it's okay to use equation 9-34 for the Nusselt number. And then we need to find the effective thermal conductivity, which is just the regular one times the Nusselt number. And then using that effective thermal conductivity, that is how you can model this convective process as conductive. And so this conduction equation shows up using Fourier's law right here. And this is the value that you get. Okay, for this last question, there's engine coolant running through a rubber tube, hose, and you're asked to find the total resistance throughout the process, the system. And we can assume that this flow is fully developed, that the temperature is uniform, K is constant, the coolant is water, the surroundings are a black body and the surface is a gray body, and that this is one-dimensional heat transfer. And so you need to, before we can find the total thermal resistance, we have to find the heat transfer coefficients for air and water, since they are not given in this problem statement. And so internal convective, forced convective flow shows up when you're trying to find the H of coolant, because it's running through the tube. And so you can find the Reynolds number and you find that it's laminar. And so using table 8-1, we can find that fully developed laminar flow has a Nusselt number of 3.6, and so you can solve for H. And then the H of the air just uses natural convection like was solved before, but this time it's for over a horizontal cylinder. And so you find H. And then for the resistance network, it's set up like this, where you have like at the surface of the pipe, or like the inside surface, and then the resistance of the pipe. And then this is like the inlet of the pipe. And then this is the surface. And so you have to find the inner area and the outer area with the different diameters. And then you can find this Ri resistance, which is the convective resistance. And then the pipe uses the R cylinder equation, and R2 uses the combined heat transfer coefficient, which you have to solve for, which uses HRAD and then the H air. And then you add those together and you find R2, which is also convection. And then the total resistances can just be added based on the individual, because they are in series. And so this is the total that you find. And that is my questions. Thank you for listening.